Good morning. Good morning. So my name is Subodh. I am a PhD student at Kansas State University. So today I'm talking about a part of my research, which is torsional testing of cement-based materials for estimating shear strength of concrete. So why shear strength of concrete? This is more of a fundamental study. So concrete, whenever we use concrete, we usually use it for leveraging its compressive strength, and the usual practice is we put reinforcement to take care of tension and shear in the members. But like this is a pretty conservative and pretty safe practice. There is no problem in it. But there are some certain structures which consist of some details where concrete is loaded in shear with less amount of reinforcement to take care of shear, especially shear. Um, so that's one of the main reasons that why we wanted to know what the exact strength of concrete is under shear. Um, so we already have several prediction models to predict the shear strength of concrete based on a compressive strength of concrete, but we don't have experimental methodology, just like how we have split tensile method for split tensile test for tensile strength of concrete or um, the concrete cylinders for compressive strength of concrete. We don't have any such method for testing shear strength of concrete. So we think that if we have that, we can that might make the designing process of structures more efficient. Uh, this is one example of such structures where shear reinforcement can be less than required. So UHPCs are getting stronger and stronger day by day, and there is a desire to minimize the use of reinforcement in PCCVs as pressurized concrete containment vessels. Um, so this structure specifically here is for nuclear reactor, as you know. So there is a base mat shear that happens, as I've shown in the figure, that is because of the hoop stress and base acceleration due to seismic load or maybe wind load. So the base part of the joint of the dome and the base mat has a high amount of shear, or you can call compressive shear in that region. And um, so this is not a practice. This is not in a common practice now to not use reinforcement in nuclear reactors, but this is research in progress, like we are doing. That there is a desire to do that. So if we are going to do that, then we need to know what the shear strength of the concrete is and how much it can bear. So that's one of the implementation of, or one of the reasons why we need to know what the exact shear strength of concrete is that we're using. Maybe the UHPC or normal concrete. So that's one reason. So these are the current or previously used shear testing methods that has been used for different materials, mostly for metals. So the first one here that you see as image A, that's asymmetric 4-point bending method, or today we call it isopescu method. So isopescu basically modified that basic test configuration into a fixture that I will come to later in a couple of slides. But that's the one which came closest to generate pure shear, because in that setup we get zero moment in the notch section in the middle, and so we think that it's very close to pure shear. The other one, S notch, is also we expect to have a shear between the two notches and expect a fracture in that part. These C and D are more of a used for testing adhesives or fibers under shear or mixed stress state. They're mainly called as an arcane taste. Then E and F the E is double shear test in prisms or concrete beams. That's pretty common to see. We expect that the shear dominant zone or shear zone is developed between the edges of the loading, like that one and that edge, and expect the failure there as a shear failure. The F is also similar, but it's in the form of cylinder. It's double shear in cylindrical form. So basically, these are two concentric cylinders, and we apply the load in the middle, and that should generate. We expect to generate a pure shear in that connecting web on the both sides. The G is sort of ideal way to generate shear, but it's very difficult to do that in practice. And H is again, that's a circular, cylindrical push-off specimen or punch-through shear specimen that has been used for cement or mortar. Now, the problem with these is like almost conclusion of almost all test methodologies except isopestivity, the first one, is that the specimen is failing in diagonal tension and not in shear. So that's a bit of an argument there. Is that really shear, or is that just in the form of bending or tension, tensile failure? Like I mentioned before, we have several models to predict shear strength of concrete, and these are some of them that are plotted on one graph to show how much the predictability of the models differ from one another. And these are derived from various geometries, like I've shown here. So this graph just shows that we have the prediction equations, but we don't really know what is the exact shear strength as the strength, the compressive strength is increasing, or is that relation, are we considering it right? So that's the motivation behind this topic. So ASTM D5379, so this is what it's called is isopesky test, that the figure one, the first test configuration of all the test picture I showed. So this is so far considered as the standard shear testing method for composite materials. And that's the closest we can get to have a standard shear test for cement-based materials to date. So there is no dedicated test method for concrete per se. The problem with this picture is, if you remember this first figure, this is basically modified in this picture. So ASTM does not specify any clamping force. So how it works is you put the specimen, the gray one is a specimen, you put the specimen in the fixture. The right half is free to move or free to slide vertically, and the left one is fixed. So you apply a load on the one that is sliding to the right, and that is supposed to generate a pure shear or shear dominant stress state in the central notched part or notched region of the specimen. The problem here is the ASTM does not provide any specific clamping force to hold the specimen in the fixture. And because of that, even the slightest clamping force does create partial fixities in the two halves of the specimen. And that sort of takes away of the advantage of zero moment at the central part, because you basically change the boundary condition of this configuration. So that's one thing. And then another problem with this is the stress state that is generated in the test region, which is the middle section, notch section. It's not uniform throughout the section or throughout the height of the specimen. And because of that, it tends to fail in bending most of the time, uh, or diagonal tension. I will come to that in a couple of slides. So to analyze several test methods that I've mentioned before and the torsion that we are suggesting to use, we use stress triaxility as a concept for analyzing those geometries. Stress triaxility is nothing but a scalar, which gives us a pretty accurate idea of what is the stress state generated at a point of interest in a specimen or in a structure. It's nothing but average stress over one meters. Um, so this is a stress triaxility space to give you, just to overlook on it. Like I said, stress triaxility is a scalar. So if we get the value of triaxility as 0, that indicates that we have a pure shear in that point of interest. If it is a negative value, that shows that we are in a compressive stress state zone, negative 1/3 being hydrostatic compression. And the positive values of the triaxility indicates that we are in tensile stress state zone. Um, so this is the fundamental that we use to analyze how the stress state is generated in different geometries and compare them with each other. The red circle that I've drawn there, that is the part that we're interested to test for concrete or cement-based material. Because we have a pretty good idea of how concrete works in compression. We have a decent idea of how concrete works in tension or bending. So that triaxility 0 part is what we are missing in our knowledge. Experimentally, we have several models, but we don't have physical experiments to prove which one is most accurate. So the plot here, the FEM analysis, again, this is the standard test configuration, the ISOPESQ, you can call it. The FEM for triaxility. So what you're seeing here is the color plot is plotted for triaxility between 0.1 to negative 0.1. That is to just focus on the shear part of the geometry. And you can see it's in the test section or test region, it's highly compressive in the middle. It starts at tension. It transits through shear, but a high majority of the section is in compression and not in shear. The S0 geometry, again, the same phenomena. We expect the shear formation or shear stress state formation in between the two notches, but as you can see in the FEM, that's highly under compression. The black shade is nothing but high negative values, more than 0.1 and more than negative 0.1. So that is in compression, and the white part is in tension. Again, the double shear in cylinders. Double shear we expect to have highly shears dominated stress state in that web. But as you can see, the path of shear stress or the pattern of shear stress state is not pretty obvious as we thought it would be. The same scenario is with the punch through shear. It's in highly compression and not in shear. This is another test setup, double shear, which is a very common to see to study the behavior of concrete in the shear. So we expect to have shear in between those two spans, between the edges. But as you can see in the FEM, the stress triaxility value is highly negative in between those regions. So that is even though the specimen is failing in that region, the stress state across the failure surface or test section is not is not shear, but highly compressive or tensile. Now, therefore, we come to torsion, because torsion is a really nice setup that once you put something in torsion, you get really uniform distribution of stress as well as stress state across the length as well as the test section. So the plot that you see here is on x-axis is the parametric distance. That is nothing but the section normalized to its length. For orange graph is for torsion, and the blue one is for the asymmetric 4-point bending, which is the standard one, also called as isofescue. There you can clearly see that for torsion, you have really smooth tractivity, stress state generated as tractivity 0 throughout the section, throughout the diameter of the specimen, as compared to what we have in a standard asymmetric 4-point bending. So that's the main advantage of using torsion for shear. So we preliminarily casted a rod of cement paste and cement mortars, the straight rod, and put it under torsion. So we expected to fail it as a straight section to be under shear, but we didn't see that. We saw helical fracture, as you see here, which is again an indication that it is still not failing in shear. So that is again the diagonal tension that is happening there. So the possibilities were the one thought was cement is very brittle material, so even minor and under shear or tension, it is very sensitive to that stress rate. So even minor air bubble or any unevenness on surface can start fracture anywhere. So to mitigate that issue, we came up with a localized torsional specimen. So the one that you see in the middle as a specimen, and to the left and the right are the sort of hex sockets to keep them to hold them in place while testing it. And we put a notch in the middle to force it to fail in that section, hoping that it will fail in a vertical plane. But again, when we tested it, you can see the crack is still on a principal plane, indicating that again it is still failing in diagonal tension and not pure shear. So to mitigate this problem, our further step or further analysis or solution to this was to add an axial stress component to the specimen to nullify the effect of the principal stresses, and so that the diagonal tension will not happen, and we expect that to fail right like 90-degree plane in shear, or at least shear dominated compression. So that's our future plan. And then once we have that, the good thing about this setup is we can then it gives us a high sensitivity to control what stress state we want to produce in that test section, because we can do the math for tractivity and decide how much axial force we want to put externally to create the stress state in the graph that I showed here. Yeah. So basically, we can pinpoint and generate any stress rate we want using that test setup by varying the axial stress component in the test. So yeah, that's how far so far where we are at, and I guess in next ACI I'll present the data on it. But thanks.